Yes. Alright, Assalamu alaikum. Yes. The quiz will cover all the topics that we started from day 1 up to electric potential. Alright, so a quick recap of what we've discussed about electric current so far. Suppose I have a wire which I'm purposely drawing as a bent wire. Now inside this wire an electric current flows. Now suppose this is a metallic wire, so the flow of current is due to the sea of electrons, and they're moving, the sea of the electrons is moving with a drift velocity. So the charge carriers in this particular case are negatively charged electrons. And the entire sea of electrons is moving with the drift velocity. And the drift velocity is generally of the order of a few millimeters per second. So even though the thermal velocity of these electrons is really large, it's 1% the speed of light, the drift velocity can be really small. Suppose current flows in this general direction. So this is the direction of the conventional current. So at each point, the sea of electrons is moving with a drift velocity Vd that is opposite to the direction of the current flow. So this is Vd, but this also necessitates that an electric field exists inside this conductor, and the direction of that electric field is anti-parallel to the drift velocity. So this yellow field is the electric field. So there exists an electric field inside this conductor which makes the electrons move ahead with a drift velocity Vd. Now this is a constant velocity Vd, it's an average velocity. We derived this velocity from the Drude's model. Now my first question is, if there is an electric field inside this conductor, then the charges must accelerate. But here we're talking about a constant drift velocity. Why is this a constant? Why are the charges not really accelerating? Sorry? Why no force is acting? There's an electric field, it must exert a force on these electrons. Where is the acceleration going? Yes. Exactly. It's the scattering of the electrons from the lattice of ions that is causing the acceleration to go to zero, and we're left with a constant drift velocity. So without scattering we will have no current. So scattering in a sense looks like an ugly thing. It causes resistance, but without this resistance we will not have a steady uniform current flowing inside this solid. So what we have is a drift velocity, we have an electric field. The drift velocity we already know for metals is given by minus NEVD, What we do know is that corresponding to this drift velocity there has to be a current density J. So this is the direction of the current density J. And J is opposite in direction to the drift velocity because we're talking about negatively charged carriers. So this current density J is minus NEVD. And since the drift velocity is a vector, the current density is also a vector. We've also seen that the current through a certain section of this conductor. So we take a cross section, a slice of this conductor, and only through this cross section or plane can we define a current. the current density is a point concept, but the current is through some area. This current, which is a scalar, is the dot product of the current density with the area vector of this sheet integrated over the entire plane. This is the current. We also know that the J equals sigma E, which sigma was defined as the DC electrical conductivity of this material. We also derived this relationship, and this was another form of Ohm's law, which was given as V delta V equals IR. So we derived the Ohm's law in the previous lecture as well. And we also noticed that this conductivity is inversely proportional to the resistivity of the material. So these are the different relationships that we came across in the previous lectures. We also noticed that this VD equals E, capital E, where this is the electric field, this is the charge on an electron. Remember, we're talking about conduction in metals, that is conduction through mobile electrons, that is the sea of electrons, into the average time of collisions between an electron experiences with the ion. So this is the average time after which an electron will experience a collision divided by the mass of an electron. So this is another relationship that we derived. So if we put this relationship into here, we'll find out what the conductivity is. The conductivity is given by minus n E squared. So the E minus E cancels out to give you a positive sign, tau over m. So this is a phenomenological expression for the conductivity of the material. Higher the carrier density, more charges are available to contribute to conduction. Higher the scattering time, which means that if this time is higher, the average time between collisions is large. So collisions or scattering events are rare, which means that the conductivity is large. So tau is large, the conductivity is large. All of these factors contribute to conductivity inside metals, and these are just relationships that we derived in the previous lecture. But the question that I would like to now ask is, how are these electric fields actually set up inside the conductor? So this is a fundamental question, and it's not generally covered in textbooks, so you really have to pay much attention to the class today. The question is, how do we produce such an electric field? So we have a battery, and I'm making a conceptual diagram of a battery. It has two terminals. One is generally thought to be positively charged. The other terminal is thought to be negatively charged, and we connect some circuit. Suppose we'll try to light a bulb with this battery, and we see that this bulb glows. Of course, there has to be some current flowing through this circuit. Where is the electric field coming from that causes the current to go through this circuit? Because whenever we have a current density, we'll have an electric field inside the conductor. And remember, here we're talking about out of equilibrium situations. Charge is not static. Charge is moving, so it's an out of equilibrium situation. There are forces acting on side the charges, even though there is no acceleration because of collision. There are forces acting on charges, so it's an out of equilibrium situation. Hence, there must be an electric field in the interior of the conductor. It's not an electrostatic scenario here. So how is this electric field produced? And this is the topic of discussion today. But before that, in order to hone in onto this concept, I would like to bring to illumination a really subtle phenomenon that is not generally covered, but will give you exceptional insight into the phenomenon of conduction. Because I realize that most of you are electrical engineers. So if you understand this concept of conduction inside simple circuits like this, I think you'll have a real edge over understanding the underlying physics of your circuits. So what I'm going to introduce now is a concept of electrical feedback. Suppose I have a conductor that is shaped into a cylinder, and some current is flowing through this conductor. The current density, which I am denoting in blue, is in this direction. This is J. So the entire sea of electrons is moving with a certain drift velocity, a few millimeters per second by the way, and it's directed towards the right, so current is also flowing to the right, and when I say current, it means the conventional current. So this is the direction of J, but the sea of electrons is also moving here, it's also moving here. So there is a J everywhere, because J is a point function. There's a current density here, a current density here, a current density here. The entire majestic wave of the sea of electrons is moving with a few millimeters per second. Now this necessitates that there must be some electric field here, there must be some electric field here, there must be some electric field here, everywhere inside this conductor E. Now suppose we're talking about steady state conditions. Steady state conditions means that the drift velocity is independent of time. It does not change with time. It has no time dependence. This means that the drift velocity is constant with time. The current density is constant with time. So this is the meaning of steady. Steady is with respect to time. Now I would like to invoke the concept that I would like to find out whether the electric field is the same in magnitude at different points inside this wire. So I would like to find out whether the electric field and hence the drift velocity and the current density is uniform. So uniform is a concept that invokes space. Steady is a concept that invokes time. So it's steady in time, this is my assumption, and I would like to find out whether it's uniform, which means I would like to find out whether the electric field here is the same as the electric field here, whether it's the same as the electric field here. Now the first question I would like to ask is what's your intuitive idea of the electric field? Whether the electric field should be the same here, 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 or should it be different? Is it uniform or non-uniform? What do you intuitively think? जी आप बताएं. हाफिज अबू बकर के भाई, क्या नाम है आपका? बताएं. Yeah, J is uniform. Ji? The electric field has to be uniform. So this is quite an intuitive answer. So the situation seems to be quite different from the flow of water inside a pipe. So if we have water and if we draw the vector field of the velocities, the water is static at the edges. It's moving with maximum velocity in the middle of the pipe. So the drift velocity in a sense of water is non-uniform in a regular pipe. This is an example of what is called a Newtonian liquid. And this flow is Newtonian flow. But the situation here seems quite different. You propose that since the current density is constant or uniform throughout the interior of this wire, the electric field has to be constant. Yeah, that it is constant. And we can actually prove it using one of Maxwell's equations. Suppose I draw a circuit or a loop, which I'm showing here as a dashed circle, as a dashed loop, as a dashed rectangle. Now this is a path inside this wire. It's a hypothetical path, no doubt, but there is a path. Now I can move along this path from A to B to C to D in this direction. And I know that since there are no magnetic fields involved here at the present, there are no changing magnetic fields, if I move around this path and if I compute E dotted with dl around this closed path, that is, I go from A to B to C to D, what must this be equal to? This is Faraday's law. What is this equal to? It has to be equal to 0 because we've derived this from the work energy principle, from energy conservation, or from the first law of thermodynamics. We've already seen this. That is, if no changing magnetic fields are involved, this is the partial form of Maxwell's equation. So this has to be correct. Now let's look at this path. Suppose the electric field on this path AB is E1. Its magnitude is E1. Suppose the magnetic field here has a magnitude E2. And both of them are pointing in the general right direction. Because current is flowing in the general right direction. The current densities are in the right direction. So suppose this electric field is E1 and this electric field here. On this section of the wire CD is E2. And suppose they are different. Now there must be an electric field here as well, and there must be an electric field here as well. So now if I compute this integral over the entire path length, will I get a contribution from the sides BC and AD? No, I will not get any contribution because here the DLs are normal to the electric field. So I will not get any contribution from this path, from this element. I will only get a contribution from this element and from this element. But if you observe here, the electric field and the direction which I am traversing the path are the same, and here the electric field and the direction which I am moving on the path are different. So this gives a positive contribution, this gives a negative contribution. Suppose this length is small l of this path, the hypothetical path that I've drawn. So this integral turns out to be E1 L minus E2 L. The dot product here is negative, the dot product here is positive. But this has to be 0. So L is a constant. This necessitates that E1 must equal E2. Inside this current carrying wire. So there is an electric field inside the conductor, no doubt about it, because without the electric field there can be no current. And this electric field is uniform throughout the conductor. Okay? G. Because then this will not hold true. There is no changing magnetic field. If there is a changing magnetic field, this does not hold true. So we are only talking about DCs, direct currents, steady currents that do not change with time. Okay, so this is a partial form of Maxwell's, of Faraday's law. Yes? क्या चीज? Assumption ही हकीकत है. एक हमने assume किया और उसको prove कर दिया Maxwell's equation से. ये हकीकत बन गई. There are magnetic fields, but they're not changing with time. I have not yet covered the concept of magnetic fields. Right at the back, pay attention here. आप जो पीछे मुड़ के देख रहे हैं, आपको भी कह रहा हूं. All right. Now this is a motivation. Now let's look at something really interesting. All right. Now these relationships should be at the back of your mind. And if you observe something here, this drift velocity is proportional to the electric field. Higher the electric field, higher the drift velocity. And as a result, higher will be the current density. So this object here, E tau over m, is a constant of proportionality between the electric field and the drift velocity. Okay, and it depends upon the medium, on the kind of material. The scattering rate depends upon the medium. This m also depends upon the medium, what kind of charge carriers we have. So generally this relationship Vd equals something into the electric field is written with a constant of proportionality mu. This constant of proportionality is called the mobility of charge carriers. And this mobility is E tau over m. Right. And this mobility also features here. This is n into E into the mobility. So higher the mobility, higher will be the conductivity. But remember that there is a relationship between the electric field and the drift velocity. This is also the Ohm's law. So this is one form of the Ohm's law. The other form of the Ohm's law is J equals sigma E. This is also the Ohm's law. So all of these are different variants and flavors of the Ohm's law. It's not just delta V equals IR. That's one circuital description of the Ohm's law. But these are more microscopic, fundamental descriptions of Ohm's law. Okay? Delta V equals ER, I would call it a circuital description. It's important because you're dealing with macroscopic measurements of voltage and current. But these are microscopic forms of Ohm's law. In fact, you have quantum forms of Ohm's law as well. Anyway, just keep this at the back of your mind. Now suppose I would like to talk about electrical feedback, as you know. Suppose I have a graded conductor. Remember, without further ado, I'm going to talk about metals. My conductors are metals. A graded conductor means that I have a wire that is conducting electricity. There's a charge, a current flowing through this wire, and suddenly there's a change in the cross-sectional area of the wire. And both of these wires are made of the same material. This is copper, this is copper. Alright, it's a graded conductor. There's a step index in the wire. So you have a thin wire of some gauge and you have another thicker wire of another gauge and you solder them together to make a nice clean connection. Still a wire, it's going to conduct current. Now suppose the conduction is due to the mobile electrons. So there are electrons that are contributing to the current. And these electrons, suppose they are flowing in this direction. So the drift velocity of the electrons in this medium is Vd1. And the drift velocity of the electrons inside this medium is Vd2. Now we'll have to determine whether these drift velocities are the same or they're different. Now this cross-sectional area is A1. This cross-sectional area is A2. Will the charge carrier density be the same on both sides? Yes, it's going to be the same because it's copper. Copper doesn't change its identity. It's still going to be N. Something 10 raised to power 28 per cubic meter. That's the rough estimate. So the charge carrier density is going to be the same. Now if I look at my expression for the current, I equals N E Vd A. So this is my general expression for the current which comes out from here. This is J times A. Now what we have is that the carrier densities are the same, the charge on electron of course is the same, and we have to determine what do we say about the drift velocity and the area. So the areas are definitely different, so we have to figure out what's going to happen to the drift velocities of these electrons. Now if you think for a minute, there are electrons coming in here. There is certain cross-sectional area A1. But overall on this surface, the electrons are, so the electrons are coming in at the interface. This I call the interface. The electrons are approaching the interface and a certain number of electrons are approaching the interface per unit time. That's the current. Then there are certain number of electrons that are leaving this entire interface per unit time. So is the number of electrons approaching the same as the number of electrons that are leaving this interface? No, they're not. The interface is this one. So if you look at this entire plane, there are fewer electrons that are coming into the interface than there are electrons that are leaving this interface, because electrons are also leaving from all of these points. And since this area is larger for this side of the conductor, there are more electrons that are leaving the interface per unit time than they're coming in. So now we have a section inside this conductor at the interface in which fewer electrons are coming in and more electrons are leaving the interface. Now, in general conditions, if you look at the wire of this kind, everywhere it's electrically neutral because electrons are coming in, the sea of electrons is moving in and the sea of electrons is receding. So every point is electrically neutral. This is the condition called quasi neutrality. All of the points inside this wire are neutral, even though charges are flowing, because charges are flowing in and they're flowing out. There's no breakdown of neutrality. But in this case, the situation is different. There are fewer electrons coming in than there are electrons going out. So when more electrons are going out, this interface should develop some charge. This charge will build up. Will that charge be negative or positive? Ab batao. Why negative? There are less electrons coming in, more electrons going out. So on a net, there are more electrons receding from this interface, moving away from this interface. कौन सा charge होगा इस surface पे? Positive charge, because there's a net deficiency of electrons, a net moving away of electrons per unit time. So this surface picks up a positive charge, and this positive charge builds up with time. It increases with time because there are more and more electrons going out. So it is depleted of electrons. This interface is depleted of electrons. Depleted का मतलब इसमें से electrons बाहर जा रहे हैं, तो इस पर एक net positive charge इस surface पे develop हो रहा है. Alright, you understand this? Now what's going to happen is electrons are coming in towards a positive surface. What's the effect of this positive surface on the electrons? Will it pull the electrons towards itself?
Yes.
Yes. So when this positive charge is developing, it's pulling in more electrons towards itself. And what will it do to the electrons on this side of the interface? It will pull them towards it. So the velocity of electrons on this side of the interface is going to drop with time. As more charge builds up, the current or the number of electrons, these electrons find it easier to come towards this interface because it's a positively charged plate. They can lower their potential energy by coming towards this positively charged surface. So they will increase their kinetic energy. This is the work energy principle, energy conservation. This positive surface will attract more electrons. It will tend to lower the potential energy of the electrons seen on this side by attracting them towards it. So more electrons, the currents will tend to rush in with the higher speeds towards this positive surface, and these electrons will tend to rush away. Their rushing away will be diminished a little bit. So as this positive charge develops, this drift velocity goes up, and the drift velocity here goes down. So this started off in a sense that both of these drift velocities were the same. When these drift velocities were the same, a positive surface started to develop. That positive surface facilitated this drift velocity, so these drift velocities increased because the electrons were attracted towards the positively charged surface. But this drift velocity decreases because these electrons are also attracted to the positively charged surface, and they will not rush away with the high speeds that were previously rushing away from it. So this drift velocity goes up, this drift velocity comes down. Eventually what's going to happen is that the current that comes in is going to be the same as the current that goes out. This means that in this region the drift velocity goes up such that this product VD1A1 increases. So this is the current I1 in this region, and in this region the drift velocity VD2 goes down such that this product goes down. A2, remember, is larger. So this product goes down whereas this product goes up such that I2 becomes equal to E1. So with the passage of time, what's going to happen is that this charge that is developed at the interface, because initially the drift velocities were the same, but there was more electrons, there was a higher number of electrons on this side, so more electrons were rushing away, so positive charge developed. But that positive charge that was developing had an effect on these drift velocities, such that it brought up this drift velocity and brought down this drift velocity, such that the product of the drift velocity with the cross-sectional area here is the same as the product of the drift velocity with the cross-sectional area here. So that the current that comes in, that is the charges per unit time, is the same as the current that goes out. Hence, the current here, once this steady state condition has been reached, the current that comes in, I1, is going to be the same as the current that goes out. And when this condition is achieved, there is no build-up of charge. Whatever charge has accumulated on this surface will remain there. It's not going to go away, it's going to remain there because that charge has built up. But this build-up of charge is necessary for this current that comes in to be the same as the current that goes out. This is the concept of negative electrical feedback. A current starts to flow. The currents are different initially on both of these sides because this area is higher. There are more electrons that are rushing away. As a result, a positive charge builds up on this interface. That positive charge adjusts the drift velocities on either sides of this interface such that the current on this side becomes equal to the current on this side. And thenceforth, after that period of time, this amount of charge remains where it is. So this is a beautiful, nice example of negative electrical feedback. I give you 1 minute just to think about this. Please think about this on your own and then I'll take questions. Yes. The first question, which is a nice question, which I've already alluded at, is when I1 becomes equal to I2, when negative feedback has played its full role so that these currents are equalized, will this charge go away or will it stay where it is? It will stay where it is. There's no reason for this to disappear. It will stay where it is. There was another question at the back. Yes. No, this is the number of electrons per unit volume. It's the same. Number of electrons per unit volume. It's the same. Yes. Because the number of electrons per unit volume is the same, but this volume is larger. This volume is larger, so this means that the number of charge carriers, the sheer number of charge carriers that are available for current is large. So more charge carriers are receding from the surface per unit time. So initially this current is larger. Alright, now the question is, okay, we have to move on. The question is, if these drift velocities, they're going to be different, right? And they're going to adjust in a way that the product of the drift velocities with the currents is the same. Now when the drift velocities are different, will the electric field be the same or would they be different? Are the electric fields the same or are they different? Akif?
It should be different.
They will be?
It should be different.
They will be different. Of course they have to be different because this drift velocity is larger here. When the drift velocity is larger here, this electric field, which I am showing in pink here, E1, has to be larger than the electric field in this conductor, E2. Because the drift velocity, the electric field in this smaller conductor has to be larger because the drift velocity is larger. Here the drift velocity is smaller, so the electric field is smaller. Look at this relationship. And it also makes sense. We have a discontinuity in the electric field because there is a surface charge here. So our general formula that wherever there is a surface that carries charge, the electric field sees a sudden discontinuity, a sudden jump in its value. It also holds here. The electric field here is larger. In thinner conductors, the electric field is larger. Remember, this is what happens in steady state conditions. So initially, these currents were different, but negative feedback enabled the distribution of charges on this surface so that these incoming currents are the same as the outgoing currents. Now suppose you have a scenario which is just analogous to the scenario of a graded conductor, is that you have a wire and then you make a junction here of two wires. So you have three wires and you solder them together. Now some current comes in, I1, and these three wires all have the same cross-sectional area. Now what's going to happen is that current must flow here and some current must flow here. Initially, what's going to happen is negative feedback is going to be set up because the amount of outgoing current is large because there are two conduits for the charges to go away, rush away. So this surface develops a positive charge. There is a slight buildup of positive charge. It could be minute, it could be tiny, but there is a buildup of positive charge here. So there is a slight buildup of positive charge, and this causes negative feedback so that the incoming current becomes equal to the total outgoing current. This is I2, this is I3. Once this charge has built up, and it might take a few nanoseconds for this charge to build up, this negative feedback is really, really fast. It might take a few picoseconds for this charge to build up. Once this charge has built up and negative feedback has played its full role, then this incoming current must be the same as the outgoing current. This incoming current is the same as the outgoing current. This scenario is not at all different from this scenario. The reasoning is just the same. Here you have two output conduits, two output channels for the current. So there is a higher likelihood of more electrons to go away from this surface. So a positive charge is built up. That positive charge then adjusts the incoming and outgoing currents in such a way that the incoming current equals the total outgoing current. And this is just Kirchhoff's current law. So Kirchhoff's current law is also a manifestation of negative electrical feedback in circuits. Now you have a proper microscopic insight into the Kirchhoff's voltage law and Kirchhoff's current law. This scenario, as I mentioned, is not at all different from the scenario that I've drawn over here. Now, another interesting example, which I really like, is that of a bent conductor. All right. I have a nice straight wire like this. Now, this is the direction of the drift velocity of the electrons. This means that the current density is pointing in this direction because the electrons are negatively charged. This means that an electric field is set up inside this conductor which is parallel to the current density and anti-parallel to the drift velocity because we're talking about electrons. So everywhere the electric field is going to be parallel to the axis of the conductor, and the drift velocity is also axial. Now so far, when you talk about circuits, for the purposes of circuits, if you draw a circuit like this, it's the same as if you drew a circuit like this. It's the same. It doesn't really matter. The geometry, the bends in the wires doesn't matter. You cannot actually build a circuit like this in real life. These sharp edges are just for aesthetic purposes. In reality, your circuit might look something like this. You have wire laid out on a table, and the wire can be hanging out in all kinds of directions. Okay? So wires are actually bent in real circuits. Now suppose you have a straight wire. In the straight wire, everything is axial. Okay? It's along the axis. The electric field, the current density, the drift velocity, they're all. Now what I would like to do, I would like to take the same conductor and give it a bend. Alright? Now how do the electrons know that they have to bend? Okay, just either raise your hand or just don't speak up. Please raise your hand. How do the electrons know that they have to bend? Yes. How does the direction of the electric field change? When an electric field changes, there has to be a change in the distribution of charges. Because charges produce electric fields, they are the source of electric fields. Once again, negative electrical feedback is at the heart of this problem. So what's really happening here is that suppose I have electrons, and their drift velocity is initially in this direction, Vd. So here, far away from the bend, the drift velocity is along the horizontal direction. Now what they see is, they see an obstacle. These electrons are moving towards the bend with the drift velocity. They see an obstacle. This is an obstacle for the electrons. Suddenly or adiabatically or slowly you bend the wire. Suppose the bending process is done suddenly. When the bending process is done suddenly, the electrons that were moving with the drift velocity towards the right, they eventually they hit their heads bang on a wall. They see an obstacle. Now what that does is that these electrons initially accumulate on this surface. So this surface develops a tiny negative charge. This is the process of charge accumulation. So there is a net movement of electrons from net deposition of electrons on this surface. Now where is this net charge coming from? That net charge must be coming from the material of the conductor. There is no charge that's flying in from space. This net charge that deposits here must be lent or by the material itself. These must be free electrons that are within the material. So there is a depletion of electrons in some other region of the wire. Okay, because the wire itself has to be neutral. So that charge is borrowed from this surface. Now what happens is that initially the electric field was pointing in a certain direction. The electric field was pointing in this direction. Remember, these are negatively charged carriers. So the electric field was pointing in this direction, opposite to the direction of the drift velocity. Now what's going to happen is that this deposition of charges is going to create its own electric field. That electric field is going to point in this general direction. This is E original. This is E new. In fact, the E due to the accumulated charges. Now in this region of the conductor, the electric field has changed from E naught. It's now E naught plus E new. So if you add this vector to this vector, this electric field is going to shift slightly upwards. So the new electric field in this region is going to point not in this direction, not horizontal, but it's going to shift slightly upwards. So this is the new electric field, which is a vector sum of E naught plus E new. So this is E naught plus E new. And when this new electric field has been set up, the new drift velocity of the electrons has to now steer its direction. It has to be anti-parallel to this new resultant electric field. So the new drift velocity shifts downwards. As a result, the electrons now steer their direction gently over the bend because charge has accumulated on this surface, and this accumulation of charge has resulted in a new electric field. That new electric field is just in the right direction, so that after this process of equilibration has finished, the new drift velocities are now pointing in the downward direction, and far away from the bend they become parallel to the axis as well. In this region of the bend, they are locally parallel to the contour of the bend. So this is another example of negative feedback, in which a charge is accumulated on the surface, and that accumulated charge has caused the bending of the drift velocities and the bending of the electric fields. Now we would like to come up with an example of how much should this charge be. This is a real practical example of how much should this charge actually be. Any questions? Yes. ऊंचा सवाल पूछें, उनको भी जवाब है, उनको because they are electrons. Good point. Sometimes I'm just generally careless, right? Alright, let's move on. One question. Yes. Yes, the current is not going to be the same. Kirchhoff's current law is not held while that equilibration is taking place. Kirchhoff's current law, Kirchhoff's voltage law are steady state principles. Okay? One steady state has been established. Now let's look at, we would like to come up with a number or with an amount of charge that is required to move a current. Suppose I have, now I'm going to change this diagram a little bit so that I can make it slightly more easier to handle. So I make a 90 degrees bend, and this is a wire that is made up of copper, which has a conductivity of 10 raised to power 8 ohmmeters inverse, roughly. Now what I would like to find out is how much charge is deposited here. Okay, so there now there is some charge that's deposited here. We know that it's negative charge. It's a negative charge here. Okay, we would like to find out how much is this charge. Suppose this cross-sectional area is 1 centimeter into 1 centimeter, and it's a uniform cross-sectional area, and the current that we would like to move inside this conductor is 1 ampere. So it's a large current, remember that, a really large current, and we would like to find out how much charge is required at this edge so that the current changes its direction appropriately. Now, in order to solve this problem, it's quite easy. We would actually like to build up a Gaussian surface. Suppose the Gaussian surface that I built up, which I'm showing as a dashed line, is a rectangle that matches the symmetry of this wire. Okay, so this is a rectangle inside the conductor. Now there has to be some electric field that makes the current flow. That electric field is pointing in this direction, right? Because these are negatively charged carriers, the drift velocity is towards the right, so the electric field is pointing towards the left. So there's an electric field parallel to the axis. And here the electric field has to be like this. Correct? If a steady current is to flow through this circuit. So a steady current is flowing through the circuit, it means that some charge has deposited here or accumulated. We would like to find out that charge. In steady state, these are the directions of the electric fields, because the electrons, these are actually moving with the drift velocity like this. So this is the drift velocity of the electrons, but the electric field has to point in an opposite direction. Correct? We would like to find out what is the amount of this charge. Suppose this electric field is E. It's going to be uniform. We know that in steady state, inside a conductor, the electric field is uniform. Okay, we know that. Now we use Gauss's law. Here the electric field is pointing out. The area of this surface is also pointing out. Here the electric field is pointing inwards, the area of the surface is pointing out. Alright? So this means that the total flux through this surface, what is that going to be? That is going to be 0. That has to be 0. Which means that this surface does not enclose any charge. This means that whatever charge is deposited, it's deposited on the outer surface. So since the flux through this Gaussian cylinder has to be 0, this means that no charge can be enclosed inside this Gaussian cylinder. So by negative feedback, if any charge were deposited, it has to be on the outer surface of this conductor. Now we would like to find out how much is that charge. Suppose this charge is really small. It is small. If it's small, we will assume that the electric field due to this charge outside the conductor is really 0. Remember, there is a large current flowing through this material. Okay? So there has to be an electric field inside this material. It could be small, but there is an electric field inside this material. And there is an electric field outside as well, because there is some accumulation of charge here. Suppose this charge is so small that there is no electric field outside. So now this is an assumption. We would like to find out how much is this charge that is developed on the outer surface of this conductor, because there has to be a charge because of negative feedback. Now we once again use Gauss's law to find out this charge. So there is a 90 degrees bend. We know that charge accumulates here, okay, on the outer surface. Now we draw a Gaussian cylinder that has one of its end faces inside the conductor and the other end face outside the conductor. Now this is our Gaussian cylinder. Once again, the electric field inside is like this, and there is no electric field outside. This is an assumption, because this charge is really small. Okay? Or we can make this end face go really far away so that the electric field is really, really small. Still Gauss's law is going to hold. Now we use Gauss's law. Here we get a contribution to the flux of EA, where this is the electric field inside the conductor. Excuse me. This is the electric field here. There's an electric field here. There it is. Just a minute, please. Alright, I will actually think more about this. I'm sorry about that. I just want to find out the amount of charge here. I would like to think more about this. I will actually look this up again, and I will come up with a proper discussion on finding out the amount of discharge in the next lecture. I promise that. However, let's look at another example of this similar metals. Now suppose I have two metals that are soldered together, same cross-sectional area. But now one metal is, say, iron, the other metal is copper. Now they have different conductivity, they are dissimilar metals, so the conductivity of iron is smaller, the conductivity of copper is larger, the mobility inside copper is larger, and the mobility inside iron is smaller. So given the same electric field, the drift velocity of the electrons will be higher in copper because the mobility is higher, and it will be smaller in iron. So look at this relationship here. If you have an electric field, the drift velocity will depend upon the mobility. Higher the mobility, higher will be the drift velocity. Higher mobility means materials that are more conductive, that have a smaller resistivity. Now copper is one of the best conductors that is known, pure copper especially. So it has a higher mobility and a higher conductivity. So now what's going to happen is that if current is going to flow through this junction, this is also an interface between two dissimilar metals. Electrons are coming in with a certain drift velocity and they're going away with a certain drift velocity. Now the electrons, there are more electrons that are going away from this interface per unit time because the conductivity here is larger. So the drift velocity of the electrons in this region, VD2, is higher initially than the drift velocity in this region. So when the drift velocity is higher, a charge will accumulate on this surface. Now what is the nature of this charge, whether it's positive or negative. It's आप बताएं पीछे, आपसे पीछे आप बताएं, चलें आप बता दें. A charge is going to develop on this interface. बताओ जी. Negative. Is it negative or positive? जल्दी बताएं. Negative नहीं होगा क्योंकि there are more electrons that are rushing away from this interface because these drift velocity is larger, the mobility is larger, so there are more electrons that are rushing away from this interface. So there is a depletion of negative charge here. A depletion of a negative charge means that this interface becomes positively charged. It develops a positive charge. Now this positive charge, as it develops, it pulls more electrons towards it. So this drift velocity, which was initially lower, it goes higher. With time, as equilibrium is being set up, it's pulled up, it's ramped up. This positively charged plate brings in more electrons towards itself. So the drift that was lower on that side is generally built up, it's ramped up because this positively charged interface is going to attract electrons. Electrons will tend to come towards the positively charged plate because they would like to lower their potential energy. On the other hand, the electrons that were moving away from this high mobility in this high mobility medium, they would tend to slow down a little bit because this is a positively charged plate and the electrons are attracted towards the positively charged plate. So with time, this drift velocity goes up and this drift velocity comes down. Eventually what's going to happen is that these drift velocities are going to come to the same level, because we know that, are they really going to come to the same level? No. What we know that I equals minus E n VD A. Now this cross-sectional area is the same. What is different are the carrier densities. So the carrier density of copper is different from the carrier density of iron. So what's going to happen is that this drift velocity is going to go up in this region. The drift velocity is going to come down in this region such that the product of the carrier density in this region, NVD, is the same as the product of the carrier density and VD inside this region. In other words, we would like the drift velocities to adjust to values such that the incoming current becomes equal to the outgoing current. And when we've achieved that, steady state conditions have been achieved. So this is another example of negative feedback. In this example of negative feedback, a positive charge develops inside this interior of this medium at the junction, which enables the incoming current to become equal to the outgoing current. And what about the electric fields? Remember that VD equals mu E. Okay? Now, alright, and we also know that the mobilities are different. The drift velocities are in the ratio of the carrier density, so the electric fields are also different. If we would like the current density J, which is minus E n VD, right? This is the current density. We would like the current density on this side of the interface to be the same as the current density on the other side. This is what we would like. So we would like the product of n VD to be the same. Alright? Oh. Now this mu is given by E tau over m. Now these mobilities are different because of the scattering rates. The scattering rates are different in iron and copper. Which one of these will have the higher scattering rate? Which one of these will have the longer tau? Copper will have the longer tau because its mobility is higher. So the key idea is that the drift velocities adjust in such a way together with the carrier density so that the current density on both of these sides is going to be the same. And the carrier density is going to be the same, the current is going to be the same because this cross-sectional area is the same for both of these metals. And remember, if in general, if you would like to have the same drift velocity in both of these mediums, in general, if you would like to have the same drift velocity in two mediums, the object with a higher mobility will require a smaller electric field. So better conductors will require smaller electric fields for conduction. Poor conductors, which tend to become insulators, require a higher electric field to conduct. This is also making sense. This is also starting to make sense. So now we've seen three different examples of negative electrical feedback inside conductors which makes current flow. One is we've seen the example of the graded conductor. There's negative electrical feedback here at this interface which develops a charge on this surface at this junction. We've seen a bent conductor and we found out that charges accumulate on the surface which make the charges steer their drift velocities because the new electric field is set up which is just in the right direction so that the new drift velocity is always parallel and along the axis of the conductor. We've also seen an example of dissimilar metals. Now the question is, will these electric fields be the same? No, they will not be the same. If I were to make a Gaussian surface through this medium, then the electric field here is pointing in this direction, it's E1. The electric field here is pointing in this direction, it's E2. And if the length of this, and if I were to find out Gauss's law here, I would have E1 into this cross-sectional area which I take to be A. And here the electric field is in the opposite direction to the surface area here, E2A. This equals the charge enclosed in this surface, which is sigma into A. Sigma is the charge density on this surface over epsilon naught. Okay, so this A goes away. There is a step change in the electric field. The electric field will change as we go from one medium to the other, and that change in the electric field, E1 minus E2, is given by this surface charge density divided by epsilon naught. Now this surface charge density has to be inside the conductor. Remember, on a bent conductor, it was on the outer surface, on the outer periphery of the conductor. Here, this charge is developed inside the interior of the conductor, along the cross-section of this conductor. So it's interior to the conductor. Otherwise, these electric fields would not be different. Because if you were to apply Gauss's law, if this is non-zero, then these electric fields have to be different. And the electric fields are indeed different inside this region and in this region. So this step change in the electric field necessitates the creation of a charge on the junction. And you can find out the amount of that charge per unit area is just given by the difference of these electric fields. Now if you would like to keep the J's constant, you will have to adjust the electric fields such that the VDs are in the proper ratio. Okay, suppose copper has an N and iron has an N. Suppose N of copper is 2 times N of iron. Now this is just a supposition. Now if this supposition is correct, if the current density has to be the same, then VD in copper has to be 1/2 of the drift velocity in iron, right? Because the current densities have to be the same. So this means that the drift velocity in copper is actually smaller than the drift velocity in iron. The drift velocity in iron is larger. Now if the drift velocity in copper is smaller, then it's half the drift velocity in iron. The mobilities, we can find out the ratio of the electric fields. The ratio of the electric fields is such that mu of copper into the electric field inside copper is, now this is the drift velocity in copper. The drift velocity in iron is mu in iron, the electric field in iron, and this half comes in here. So the electric field inside copper divided by the electric field inside iron has to be equal to 1/2 of the mobility inside iron divided by the mobility inside copper. Now if the mobility in copper is larger, then this number is smaller than 1. So the electric field inside copper is smaller. And the ratio is given by this. So higher mobility materials, once steady state has been established, they result in smaller electric fields. If I had a wire that is made up of copper and was carrying a current of 1 ampere, there is some electric field inside this medium, E1, E copper. Alright. Now I have a wire that is made up of lead, a poor conductor which has a smaller conductivity. The electric field inside this medium has to be larger for the same amount of current. If I have a superconductor wire, like suppose I have niobium tin. It's a superconductor that has infinite conductivity, zero resistivity. In such a medium, no electric field exists and it will carry a huge amounts of current. And if no electric field exists, there can be no potential drop across this wire. Remember that inside this medium, inside copper, if there is an electric field, there has to be a potential drop across A and B. If I were to find VA minus VB, this is going to be equal to minus this electric field inside copper, dotted with DL, as I move from B to A. Now this electric field does exist. So these points will not be at the same potential. Even though this electric field can be really small, but this potential still exists. So if you have a wire that is carrying current, there will be a finite potential between different points inside this wire. A finite potential difference. Okay? So whenever there is conduction through a medium, there is an electric field that is set up. Now the question is, how is that electric field set up? Because electric fields require charges. Where are those charges coming from? From the battery? Now I would like to spend the last 2 minutes on posing a question. And we'll take up that question in the next lecture. So what we've covered so far is that whenever there's conduction inside a conductor, an electric field has to be set up. And there's negative electrical feedback that necessitates that Kirchhoff's current and Kirchhoff's voltage law are satisfied. Everything is adjusted, the electric fields are adjusted in such a way that the current coming into a node is the same as the current that is going out of the node in steady state conditions. So a negative electrical feedback is at the heart of all of this. Now the question is, if you have a wire like this that is carrying current, there's an electric field that is set up, where is that electric field coming from? There must be some charges somewhere that are producing the electric field. Okay, so let me draw a diagram and I'll finish on this diagram. Let's take an example of a battery. Suppose I have a battery, positive charge terminal, and a negatively charged terminal. And I connect this through a series of two wires to an electric light bulb. What's going to happen to the bulb? It's going to glow. This bulb glows, which means a current is flowing through this circuit. Now since a current is flowing and the current is due to the flow of electrons, because we're talking about metals, let me draw the drift velocity vectors, which is the vector field inside this circuit. So here the electrons are flowing like this. So yellow represents the drift velocity of the electrons. So they will bend here. Some surface charges develop here due to feedback which cause this drift velocity to bend. Here the drift velocity ideally should be along the axis of this conductor. Here it will bend again because some surface charges develop here. It's going to bend, right? So this is the direction of the drift velocity. You're going to bend here again. Bend here again. And we're not concerned about what's going to happen inside the battery for a moment. We'll forget what's happening inside the battery. We're going to deal with batteries later. It's a very important concept. So this is the direction of the drift velocity of the electrons. There has to be therefore an electric field that is set up inside this conductor because this material has finite conductivity. Vd equals mu E. So there has to be an electric field. Now, what direction is that electric field going to point in? It's going to point opposite to the drift velocities because these are negatively charged electrons. So there's going to be an electric field here, an electric field here, an electric field here, and this now represents the electric field. Now the magnitude of this electric field is the same everywhere. In steady state, this electric field cannot change, otherwise we'll have time varying conditions. The drift velocity is the same, it's uniform, so the electric field has to be uniform. So an electric field has to be set. Now the central question is, who sets up this electric field? Where is this electric field coming from? Yes. The holes are created by the flow of electrons. No, the electrons. So the first idea are holes. Then what do the holes do? There are no holes inside this medium. Whenever electrons are flowing, these electrons are free electrons. They do not create any holes. They're all, electrons are still there. Those are hand raised, yes. On the? On here, charge accumulation here, right here. So some positive charge here, some positive charge here, some negative charge here. Like this. But these charges are really, really small. So the effect of these charges, they cannot change the electric field. Remember, see, the electric field is changing its direction, but this electric field is significant that it cannot be produced by these minute charges. So one, the charges on the bends, these are not contributing to the electric field. Neither are there holes because there are no holes inside this system. So any other idea? Yes. The potential difference across the terminals of the battery, what did you have to say? But where is that potential difference coming from? They're not moving backwards and forward. The electrons are moving, the sea of electrons is moving with a drift velocity of a few millimeters per second. The entire sea of electrons. And this wire remains electrically neutral. So the entire sea of electrons, it's coming in and it's going out. So the entire wire remains electrically neutral. So there's an entire big majestic sea of electrons that is moving with a drift velocity of a few millimeters per second. And whatever sea of electrons comes into the wire goes out. So the wire itself remains electrically neutral. And these electrons are not moving in random directions. There's a directed motion. Any other ideas?
Resistance.
Between the ions and the? No, but that averages to zero because an electron is surrounded by positively charged ionic cores from all directions. So there is no mutual attraction or repulsion between the ions and the electrons. Yes? The electromotive force? Okay, which is coming from these positive terminals and the negative terminals. So, alright. So the question is whether this electric field is coming from the battery. That's your suggestion, right? So the proposal is that this electric field that is developed here, the pink electric field, is coming from the battery. Because this terminal of the battery is positively charged and this terminal of the battery is negatively charged. Now this is a proposal. Let's see if this proposal holds water. The question is that this is an electric dipole. Okay. You know that this is an electric dipole. The direction of this dipole is this. It's from the negative to the positive charge. From this terminal is positive, this terminal is negative. This has an accumulation of positive charge, this has an accumulation of negative charge. Can these electrodes of the battery, which you call an electromotive force, produce such an electric field? Now we know that if you have an electric dipole, the electric field from an electric dipole has a certain distance dependence from the dipole. What is that distance dependence? If you move away from the electric dipole, will the electric field be the same? It's going to drop off. And what is that drop off proportional to? It's 1 over R cube. So now if you have this battery, the same circuit, a battery here and a bulb, and then we have a battery here and a bulb which is now further away from this battery. Now we increase the distance. Will this bulb glow any weaker? Will the glow here be weaker? No, it's the intensity or luminosity of the glow of this bulb is going to be the same as the luminosity of the glow of this bulb. Now if the electric field inside the wire were coming from these terminals, then indeed this bulb should glow dimmer because it's further away from the dipole. But this is not the case. Another point is that if you observe here, the electric field due to this positive terminal is pointing in this direction. The electric field here is pointing in this direction, right? Here the electric field due to this electric dipole is pointing in this direction, right? So this is what the electric field of a dipole looks like, remember? Correct? Here the electric field is pointing in this direction, fine. Here the electric field due to this dipole is pointing in this direction, fine. But what if I change the circuit and I make it slightly convoluted in this fashion? Practically, will the bulb still glow? Yes, it will still glow. But if you look at the electric dipole field due to the battery, at this point, the electric dipole field here is still going to point in this direction. But the electric field is pointing in this direction, but still we have the electrons that are drifting in this direction. And the current is in this direction. And still the bulb is glowing. How is it possible that we have an electric field in a direction that is normal to the actual drift velocity of the electrons? The drift velocity of the electrons has to be collinear with the electric field. So this bulb still glows. So hence our concept is that this electric field is being created by the battery, does not hold water. So we have to find out what is the origin of the electric field inside the conductor. When a circuit is connected to a battery, indeed electric fields are set up. But what's the origin of that electric field? And where are the charges inside this conductor that produce the electric field? So we'll take this question up in the next lecture. Thank you very much.